Let's walk through a theoretical calculation now that we're going to be testing in class. Our question is, what is the longest straw you can drink from? Let's apply our expression for hydrostatic pressure to this problem and see if we can figure out the longest possible straw that we could drink from. Our first assumption is that we're going to be drinking water, and we pick water because we know that the density of water is 1,000 kilograms per cubic meter. So let's make that part of our list. 1,000 kilograms per cubic meter. Okay, our next assumption is that the straw is going to be perfectly vertical. So let's make a sketch of us and our tall straw. So let's make us, here we are, let's put us up on a very tall chair. Let's have us drinking out of a straw that goes down to a cup of water on the bottom. Okay, so there's our straw going up to our mouth. Let's write our equation for hydrostatic pressure. P2 is P1 plus rho GH. Our rho is okay, we figured that out. G is 9.81. H is the thing we're trying to figure out. P2 and P1. P2 stands for the pressure at the bottom. So that's down where our water is, P2. P1 stands for our pressure at the top. That's where our mouth is. What is P2? Well, where our straw goes into the cup is open to the atmosphere. So P2 must be atmospheric pressure. That's 1.013 times 10 to the 5 pascals. What's P1 going to be? Let's see if we figure something out as we think. So the next thing maybe we can do is let's rearrange our equation and let's solve for H. So P2 minus P1 equals rho GH. Divide both sides by rho times G. We get P2 minus P1 divided by rho times G. So here's an expression for the height of the straw for our tallest possible straw. Okay, so we see if we want to get our tallest straw, then we have to have our smallest pressure, P1. So if we want our height to be big, we need to have this pressure to be small. What's the smallest pressure we could possibly have in our mouth? Well, that pressure would be 0. If we could have a perfect vacuum inside of our mouth, then we'll get the tallest straw that we could possibly have. So let's let P1 equal 0. So now in our expression for our height, we'll fill in that P2 we said was P atmospheric. We'll divide that by rho times G. So let's fill in our numbers. H is P atmospheric, 1.013 times 10 to the 5 pascals, divided by rho, 1,000 kilograms per cubic meter, times G, 9.81 meters per second squared. Put all that through the calculator, and what we're going to see is that we get the height of our tallest straw is 10.3 meters. That's actually really tall. 10.3 meters is about 30 feet. That would be about equivalent to the 3rd story of a building. So in theory, you could get on the 3rd story of a building, put your cup down on the floor, make a perfect straw, and you could drink out of that straw. We're going to try this out in class. We're going to build these tall straws, see who can get the longest, and how close can we get to 10.3 meters. Discussing ways to measure pressure, and one of the devices we use to measure pressure is called a barometer. Our picture here is an old-fashioned barometer. This is the kind that we had in my home when I was a kid. Maybe some of your grandparents have these, although maybe you don't have them in your own homes right now. You could look at the barometer and you could tell if the atmospheric pressure was high or low, and that would give you an indication if good or bad weather was coming. To make a barometer, what you do is you start with a glass tube and you completely evacuate it. You get the pressure in the tube to be 0. Then you take your tube and you turn it upside down and you immerse it in a dish of liquid. Typically, the liquid we use is mercury. Now, if you're wondering, isn't mercury toxic? The answer to that would be yes, absolutely, it is toxic. We're going to talk about why we use mercury. But mercury is a liquid. That's kind of the key part here. So we've got our evacuated glass tube here. It's in a dish of mercury. This side of the dish is open to the atmosphere, so the liquid at this level must be at atmospheric pressure, and then the pressure in the tube is 0. That causes some mercury to rise up in the tube. Then we can measure this height h, and this height h is going to give us a way to calculate the atmospheric pressure. We'll do that on the next slide with our equations, but this is fundamentally how a barometer works. Nowadays, we don't really use mechanical barometers. We just have apps on our phone. The way those apps work is that they link to weather sites that do use mechanical barometers. Here's what we know now about pressure to see how we use a barometer to calculate atmospheric pressure. The first idea we apply that any 2 points at the same height in the same fluid have to have the same pressure. So the pressure here, 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 all along this line, all has to be equal pressure. I'm going to pick 2 points. I'm going to represent them with a dot. I'm going to put one dot at the bottom of that column of fluid, and I'm going to put one dot over here. I'm going to call my dots dot 1 and dot 2. I'll call P1 over here, so this is my dot 1, this is my dot 2. So point 1 has pressure P1, point 2 has pressure P2. How do we write down both of those pressures? So my pressure at point 1 is open to the atmosphere, so it's equal to atmospheric pressure. Okay, that's the thing we're going to try and measure. P2 is at the bottom of a column of fluid. We know how to write this now. This is using our equation for hydrostatic pressure. The pressure at the bottom is equal to the pressure at the top at 0, plus the pressure due to the column of fluid, and that's equal to rho times g times h. Now P1 equals P2 because they're at the same height in the same fluid. So that's a restriction we're going to apply a lot of times. So let's set those equal. That means P atmospheric equals P2, which is rho times G times H. So if we measure H and we know the density of the fluid in our barometer, we can just calculate our atmospheric pressure. This actually leads to a new definition of pressure that's called millimeters of mercury because we use mercury in the tube. We're going to talk more about that in class. Let's think for a moment though, why don't we use water in a barometer? Mercury is toxic. Water is not toxic. It wouldn't be problematic if we broke it. Let's think about this. If we had water in the tube, then atmospheric pressure would be 1,000 times 9.81 times H. We'd get H to be the 10.3 meters that we saw with our tall straw. This would be impossibly tall for most homes. You just couldn't practically have a barometer like this. Okay, so we'll look at this when we're in class. We'll think about the density of mercury. We'll look at the height of that typical tube in mercury, and we'll talk about why we use mercury and our units, millimeters of mercury.